Right, Frank is now with us and it's almost 5 o'clock, so I shall hand over to him and let him introduce Alan.
Right.
Hope you all enjoy the webinar.
Okay, thank you, Anna. Well, welcome to April's Shack webinar. This is something we've been running monthly almost since the crisis began last year to sort of help promote the history of chemistry while we can't meet in person. And I think it's fair to say they've really been a really successful program. So we'll certainly keep it in some sort of form once we're able to sort of get back to real live meetings. This is being streamed both on Zoom and on YouTube. If you've got any questions on Zoom, please put them in the chat box and I'll call them out after the seminar. If you're on YouTube, if you put the questions on the YouTube facility there, those will be relayed to me. I'm afraid I won't be able to sort of invite you to contribute if you're on YouTube. And one further thing about YouTube is we've now got a proper YouTube channel. At least we've got more than 100 people subscribing to it, but we can always do with more subscribers. So if you feel like subscribing and you don't already subscribe, please feel free to do so. So it gives me very great pleasure to introduce this afternoon's speaker, Alan Rocke, who is Distinguished University Professor in the History Department of Case Western University. He is known primarily, I suppose, for working on 19th century French and German chemistry, though not solely, particularly writing on the history of atomism, the history of molecules, about working on such figures as Cole, Kekule, Liebig, Hertz, etc. And today, continuing that theme, he's going to talk about Meyer and Mendeleev. Alan.
Thanks very much, Frank. I'm very grateful for the invitation, and I thank everyone for being present. I do want to say that what is to come in this presentation is very much a collaborative effort with my excellent colleague, Gisela Boeck. And Gisela and I have recently handed over our materials, our finished materials, to the press. And this will come out in 2 editions, a German and an English edition, studying Lothar Meyer's early work in the periodic system of the elements, including a full translation, or in the German case, a full reproduction, edited reproduction of Lothar Meyer's first edition, Modern Theories of Chemistry. So that should be out hopefully by the end of the calendar year. And as I say, a lot of what is to come in the next half hour is joint work between myself and Gisela Boeck. So I first want to, everybody knows the periodic table, but I wanted to put it up for you and to emphasize that, in fact, there are going to be what I have to say, particular emphasis on the distinction between the main group elements and the transition metals. And here the main group, of course, are in green, and the transition metals are in blue. And I'm going to maintain that color coding. So keep that in mind. The main group elements will always be green colored, transition metals in blue. And of course, the distinction is that the main group elements show clear valence regularities and clear family resemblances. So the alkali metals, the alkaline earth metals, and on the other side of the transition metals, boron, carbon, nitrogen, oxygen families, and the halogens and noble gases. So clear family resemblances, clear valence regularities. Less so, of course, with the transition metals, less clear both in valence, and these family groups show less clearly marked family resemblances. And the reason I make this distinction now is because it was clearly also understood, empirically speaking, in the 19th century, in the period that I'm going to be talking about. So let's get back to the 1860s. And in order to play this game, you need basically three things. You need a recognized set of chemical elements. You need the fullest possible understanding of each of their properties, and a reliable and precise method or methods to determine their atomic weights. All three of these factors were moving targets in the 1860s. Year by year, more information was coming out, discoveries were made, and so on. It was a bit, if you were trying to solve the periodizing game, it was like solving a jigsaw puzzle with an unknown number of pieces missing, some of the existing pieces imprecisely cut, and the shape of the final picture unknown and indeterminate. Not only that, but these factors were also changing year by year. So it was a difficult game to play, especially in the early 1860s. So how did all this look in the 1860s? Today we have almost 120 elements, but half that number were known, about 60. No noble gases, nor any of the radioactive elements other than uranium and thorium. And the properties of uranium and thorium were imperfectly known. There were few rare earth elements that were securely characterized. A number had been detected, but their properties were not well understood. Of course, subatomic structure was unknown. As everyone knows, even the atomic theory itself was contested in some quarters, in some measure. So the only readily periodizable elements in the period we're talking about were the main group elements up through bismuth. After bismuth, of course, you get into the radioactive elements and transuranics, and the transition metal elements. So here's a periodic chart pruned appropriately for the 1860s. I've left off hydrogen because nobody has ever known exactly where to put hydrogen. Helium and the rest of the noble gases are gone. They were not known. And elements after bismuth. So it's basically lithium to bismuth that we're talking about. And most of these elements, almost all of them, were known in the 1860s. And a few more were known, but they were thorium, uranium, and a small handful of rare earth elements, but they were most of them were insecurely characterized. Well, the two earliest formulators of complete systems, periodic systems of the elements, of course, were the German chemist Lothar Meyer and the Russian Mendeleev. And as you all know, most of the historical work that has been done on this problem has focused on Mendeleev. The volume of historical work on Lothar Meyer is much less. And so Gisela and I have concentrated on that interesting subject. As far as I'm aware, there was only one time that Meyer and Mendeleev met. Here's Lothar Meyer, here's Mendeleev. And this was on the occasion of a meeting of the British Association in 1887. And so this was taken in Manchester. Here's Henry Roscoe here. As far as I'm aware, this is the only time, at least I know of, that they met personally. The interesting thing about this photograph is here is Lothar Meyer's wife, Johanna Meyer. It's the only photograph of chemical colleagues that I'm aware of that includes a spouse, a non-scientist spouse. And I think that's very interesting. And I don't think we'll ever find out how she got into this picture, but I think it's a very interesting fact. So a quick, overly quick couple of generalizations about prior historical studies of the rise of the periodic system of the elements. And again, this is overdrawn, and I don't mean to cast aspersions, but when treating a single protagonist, and nearly always this has been Mendeleev, there is an understandable pull towards the model of the solitary genius. And when treating several protagonists, there is a very understandable pull towards an emphasis on priority disputes and rivalries. And I can't say that Gisela and I have been immune from these pulls, because as I say, they're very understandable, but what we've tried to do is emphasize more this problem as a diachronic interacting group. What did Mendeleev and Meyer learn from each other? What did they, contrariwise, what did they do independently, roughly simultaneously and in parallel? And how did the flow of new and ever better data year by year influence the development of each of their various systems, the periodic systems of the elements, as one followed the other? So a quick review. Most or all of you have seen this. This is Mendeleev's first periodic table in draft. This is a sketch he made for himself. It's rotated 90 degrees from the way we think of the periodic table. It's dated, and if you convert the date into the Gregorian calendar, it's the 1st of March, 1869. He published this in exactly this form. It first appeared in print in a Russian journal in May of '69 and in a German journal in July, in the summer of '69. So I've turned it here, I've turned it 90 degrees, so it makes more sense to modern eyes. And you see he has included a small handful of rare earth elements. Most of them have question marks, and rightly so. He has included also uranium and thorium. There are some interesting qualities to this earliest complete published periodic table. Okay. So I've reproduced the table in the lower half of the screen with green for the main group elements and blue for the transition metals. And I wanted to point out a few interesting facts here. These are well-known facts, actually. In the boron group, he has a question mark where a new element would eventually appear, namely gallium. In the carbon group, he has another question mark where a new element would ultimately appear, germanium. A question mark after calcium where scandium would appear. And so these were explicit predictions, and he did make these predictions quite explicitly, even in this first periodic table. There are also some rather odd aspects. Here are the alkaline earth metals, and they're separated into two separate families with rather odd accompaniments: zinc and cadmium on the left and lead on the right. And I say these were rather odd connections, odd family groups. They're odd with modern eyes, but they're also odd with 1860s chemical eyes. They really didn't fit well in the context of the 1860s, and it's not clear to any of us why he made these assignments of family groups. He also put uranium and gold with the boron group, and again, looking at it from the 1860s, it's not clear why they could fit there, and he didn't justify these. He did, however, make these three important predictions, these famous predictions, and these predictions were fulfilled. He made them in 1869, but in much greater detail in 1871. And by 1875, the first of these appeared, gallium, and then scandium, and then germanium, the three famous predictions of Mendeleev. And here are his predicted data. The data that was found was very similar to that, very, very close. And so this is one reason he became as justly famous as he did. Let's now turn to Lothar Meyer, and here are the title pages of his first and second editions of Modern Theories of Chemistry. First edition, 1864, 5 years before Mendeleev's first chart, first periodic table, and 1872, 3 years after Mendeleev's first table. So in 1864, in the first edition, he presented 3 different partial periodic tables, and this is the famous one. These are essentially nearly all of the main group elements of 1864, and it is a periodic table, although he didn't say that. He left it implicit, but it is periodic table because you can see the valences here on the top labels of these columns. The columns are the family groups: carbon, nitrogen, oxygen, the halogens, the alkali metals, the alkaline earth metals. He transposed the tellurium and iodine atomic weights because tellurium is heavier, but it comes before iodine. It needs to because tellurium is an oxygen-like element and iodine is a halogen. He also left an open space here where germanium would ultimately appear, and he has an implicit prediction of germanium's atomic weight, but it's only implicit. You have to add 44.5 to 28.5, or subtract 44.5 from 117.5 to get the predicted atomic weight of germanium of about 71. He left all of this implicit. He left it for readers of his book to infer. And so it's not a full periodic table, it's a partial periodic table, and he did not make an explicit claim for periodicity in this at this time. But it was, I want to say it was very early in this period, 1864. Things were still being discovered, and you'll notice that the boron group is completely missing. But there are good reasons for that fact. The boron group was poorly understood at this time. The group is boron, aluminum, gallium. I'm missing one. Boron, aluminum. Which one am I missing? Anyway, gallium.
Indium.
Gallium, indium, and thallium. So boron, aluminum, gallium, indium, and thallium. Indium and thallium were just discovered very recently. And here, was that you, Gisela? Giving me a little help?
Yeah, I said only that this were indium, thallium.
Yeah.
In the boron
Okay.
group. Okay.
Were poorly understood at this time as far as their valences. So it's is everyone, are you with
I think
me?
we just lost you briefly, Alan, but are you back again?
Okay.
Right.
So we're on again. This is what Meyer did in 1864 in his first edition. Now, it was not unknown to Gisela, but this was a surprise to me, that Lothar Meyer's 1864 first edition was translated into Russian. It came out in a Russian edition in 1866, St. Petersburg. And the question is, this was 3 years before Mendeleev's first published periodic table. The question is, did Mendeleev read Lothar Meyer, first edition in Russian? He certainly could have. And it's important to recognize that there were many, many Western chemistry monographs and textbooks that the Russians translated in this period in the 1860s. So the Russians were very interested in translating Western works into Russian, including Meyer. Did he read this before 1869? Was he influenced by it? And we can't answer that question, but there are interesting circumstantial cases. He was very careful. Mendeleev was very careful subsequently to cite every early predecessor of the periodic system of the elements whose work he had read prior to 1869, with one exception. He never mentioned his major rival, Lothar Meyer, as a predecessor. When he mentioned Meyer's early work, the only thing he ever said about it was that it wasn't really a periodic system at all. So you can argue that it's likely that by circumstantial evidence that Mendeleev read Meyer, or at least perhaps he was embarrassed to say that he hadn't, because it was available to him in Russian. Was he influenced by it? We can't really say, because his 1869 table was very different from Meyer's partial periodic table of 1864. So if he did get a hint from reading Meyer's first edition, he went off in very different directions, which suggests predominantly parallel and independent thinking. Of course, not every interesting historical question is answerable from surviving documentation. So when Lothar Meyer read Mendeleev's first periodic table, he got busy. He had actually prepared a complete periodic table, but only in draft in 1868. So he knew that he had been scooped. He prepared this paper published in Theorien der Chemie in December of that year, about 6 months after Meyer's first publication. And this then is his first complete periodic system, published in December of 1869. Now here I've turned it around 90 degrees so we can read it a little bit better. And it's still rather difficult to interpret with modern eyes, because it's what we want to call a short form system, a short form table. For example, here in the nitrogen group, you have nitrogen, phosphorus. You do have arsenic and antimony and bismuth, but you also have vanadium and niobium and tantalum. And so it's a rather odd look from a modern perspective. Here I want to compare Mendeleev's long form table, where we have nitrogen, phosphorus, arsenic, antimony, bismuth, and this new kind of short form table, which Meyer pioneered. Later, Meyer would make a claim that this was an important novelty that he had priority for over Mendeleev. That he loved this short form table, he thought it had advantages, and he said he was the innovator. And
Sorry, we've lost Alan again briefly.
Of Meyer in the course of 1869. And it actually was published in, I'm losing you again.
You come back.
does generally come back, Frank, if it drops out. Just give him another 30 seconds, hopefully.
Okay, are you back?
Yes,
Yeah, we're back.
Okay, I'm sorry for this. I just wanted to give you now another look. Are you still with us? Hello?
Yes, we are. Yes.
Okay. Another look at this lithium to bismuth table. And I wanted to point out that the transition metals interrupt the periods. So potassium, calcium, and then 10 transition metals before you get back to these horizontal periods, gallium, germanium, arsenic. This is the modern table, of course. The transition metals interrupt the periods. In the short form table, and this is a modern table, lithium to bismuth, so-called short form table, the blue transition metals don't interrupt the periods anymore, they interrupt the families, the vertical columns. And so here's where you get nitrogen, phosphorus, vanadium, arsenic, niobium, antimony, tantalum, and bismuth. And I showed this short form modern table to an inorganic chemist of my acquaintance. And he said, you know, this is really very interesting and actually quite valuable because there are family resemblances here. The vanidates are similar to the phosphates and arsenates, and permanganates similar to the perchlorates, and so on. So the family resemblances in the triads of transition metals do show family resemblances, and they fit into these larger families, nitrogen, oxygen, halogen, and so on. So it's actually quite an interesting way of arranging the periodic table, and maybe even a more obvious kind of array because it's more close, it's closer to a rectangular array. Now here again is a modern table, lithium to bismuth, but we've rewrapped it so as to keep the blue transition metals together and the green main group elements together as well. This was Meyer's short form format. And here is his 1869 at the top, the 1869 table, and the modern solution, if it were, to the puzzle. And you see it shows very strong similarities. Well, of course, Mendeleev continued to improve his table. Here's his 1871 table. And here it is now for the first time in a short form format. Meyer thought that Mendeleev had gotten this short form idea from him, but actually we know that Mendeleev had developed it independently and in parallel. And here's what that Mendeleev 1871 table looks like in a clearer way for modern eyes. You see he has more elements than Meyer had, including a lot of hypothetical new elements with question marks, but also rare earth elements, erbium, lanthanum, and so on, thorium and uranium. So he included a lot of elements, several elements that Lothar Meyer hesitated to include, simply because those elements had insecure characterizations of valence and so on. This is what Mendeleev's short form table looked like in 1871. The next year, Lothar Meyer came up with his second edition with a revised periodic table. This is actually very similar to what he had produced in 1869. And this is what it looks like in a more clarified form. And again, it's a very interesting table if you look at the details. If you compare it to the modern table, lithium to bismuth, it is virtually identical. What Meyer did not have in this table, but predicted, and he predicted actually atomic weights as well, scandium, gallium, germanium. He didn't put yttrium and lanthanum here, because he just didn't trust what was known about yttrium and lanthanum at the time. He didn't feel like he could include it in the periodic table at all. But he also left holes for hafnium, technetium, and rhenium. Now, I realize that it's somewhat hazardous to compare a periodic table from 1872 to a modern table because one is guilty of a certain kind of presentism when one does so. But I do want to suggest that Lothar Meyer had good reasons for all of these assignments, and he discussed all of these assignments in his book. And so one can argue that making this kind of comparison is a truly historicist way of understanding, in some ways, the superiority of Lothar Meyer's work in 1872 to what had gone before. Well, if you talk about superiority, you have to ask, well, why did he make these assignments that proved to be more successful than Mendeleev's? What was it that gave him the advantage over Mendeleev? And one can of course say he maybe was simply a better chemist. I hesitate to make that statement just flat out, but he did have an advantage in a particular heuristic technique that he used, namely this plot of atomic volumes as a function of atomic weight. So atomic weight is along the x-axis, the horizontal axis. Atomic volume is on the y-axis, and you see the periodicity is very clear. Not only is periodicity clear, but the details of the visual chart helped him to make certain assignments that were superior to the assignments of Mendeleev. The irony is, and again, this was something that was new to us. The irony is that Mendeleev himself had also developed a plot of atomic volumes as a function of atomic weight. The only difference is that Mendeleev had not succeeded in putting, or did not choose to put it in a graphical way. The actual visuality of a graph helped Lothar Meyer make superior assignments. Mendeleev, who developed the same data, developed it only in a verbal way, in a chart, and not a visual graph like this. And we think that the visuality of this graph had superior qualities. Here's a detail. So I'll wrap this up and suggest some findings from our study. This is well known. Mendeleev was the first to publish a complete periodic system of almost all the known elements, and he very rapidly improved it thereafter. He made detailed predictions of yet undiscovered elements that brilliantly succeeded. He certainly deserves his fame. Lothar Meyer's work was essentially independent. Some parts were substantially earlier, and his published systems were consistently superior to earlier efforts, including Mendeleev's efforts. The short form table that I've shown you and the atomic volumes correlation were actually developed independently and arrived at in parallel by Meyer and Mendeleev. So they learned from each other, but also followed their own paths. Like Pasteur, Mendeleev's renown was justly earned, but he also knew how to cultivate it. Meyer was not as good at the latter skill. So in summary, who wins priority is not a helpful historical question when it forms the dominant focus of inquiry. Rather, we tried to focus on what was each person's pathway, what did they learn from each other, what did they develop independently, and how did they react, how did they respond to the continuous and ongoing stream of new data? What was the role of heuristic tools, such as atomic volumes? And in what ways was the visuality of a graphic form better than verbal or chart form in the atomic volumes correlation? so that superior heurism may be attached to unfamiliar formats for the periodic table, this interesting short form format. And also we want to emphasize just and admire how much can be done with how little, given from a modern perspective, given persistence, cleverness, and imagination. So thank you for your attention, and I'll stop my screen sharing.
Thank you, Alan. That was super. Not sure about the sound, but you can see the hands clapping. George got a couple of questions, but I shall still exercise my normal chair's privilege and ask the first one. And that it relates to something you said very early on about nobody having any idea of subatomic divisions of atoms. I'm just wondering, what did Meyer and Mendeleev think these elements were? I mean, are they behaving in an entirely operational way, saying there's something called iron or something called gold, if you do this with their numbers, you get this? Or did they have some sort of idea of what they're actually dealing with as a sort of physical entity?
This is a question that exercised Meyer greatly. So he was interested in what can be known about the atoms, how much can be known about them physically, chemically, ontologically. He was a firm believer in the ontological reality of these atoms, and he even speculated considerably on subatomic structure. He was absolutely convinced that atoms were not the fundamental particles of nature, that atoms had more fundamental particles inside them, and he adduced various kinds of evidence to support that idea. He wasn't the only one in the middle of the 19th century to suggest that atoms had subatomic structure, but he went further maybe than anyone else in his ideas, fruitful ideas about the possible substructure of atoms.
Okay, thank you. So first question, Eric, you can unmute and ask. Eric Serre.
Hi, Alan. Thank you for a superb lecture. Many interesting new things you've uncovered. Can I ask you about what you said were the odd assignments of zinc and cadmium? I'm wondering, just are they really odd? Because surely the valences of those two elements being the same as the alkaline earths would not make those so odd, especially in the light of what you said later about transition elements showing similarities with main group elements.
Well, there's something to what you say, very much supports actually, as you say, about what I was talking about, the family resemblances in the short form table. But you can make a distinction, I think, between the alkaline earth elements as a group among the main group elements and these secondary similarities, for example, in zinc and cadmium. I would like to maybe suggest that they were not immediate family, but cousins.
Yeah.
And that's, they were a little bit more distant than the traditional family of the alkaline earth elements.
Certainly, yeah. Yeah, just a slightly different point now, if I may. Your comments about the short form table and the fact that Meyer claimed that was his own, that's new to me. It's very interesting because there have been a couple of recent papers claiming to reconstruct the way that Mendeleev made his predictions. And in trying to do that, and in fact, Carolina, who I think is here, is one of those papers. Bill Jensen is another one. In doing that, it turns out that the use of the long form table is better than the short form table. I wonder if you have any comments on that.
I absolutely agree. And it's really what I was trying to imply in shorthand when I say that superior heurism applies to different forms. That is, you can use different forms of the periodic table in different heuristic respects. And in some cases, certain forms give you better heurism, and in other cases, another form gives you a better heurism. It depends on what you're looking at.
Yeah.
Okay, the next is from Gary Patterson, who's on YouTube, so I shall read this out. Gold was characterized by gold-free chloride, like the other Bohr elements. Meyers said was more like Crookes. I think that must be Crookes' 7-group version published in 1868. I think it's a comment more than a question, actually.
He does mean Crookes, actually.
Oh, he does mean Crookes, does he? Okay, sorry.
Yeah.
So this is very similar to the previous question. And again, I'm not denying a family resemblance, but it does seem curious, at least to Gisela and me, that Mendeleev separated a clear category that was clearly recognized in his day of the alkaline earth metals into 2 separate categories and added these other elements at the bottom.
Okay, Guillermo Restrepo, sorry if I mangled your name.
Yeah, no problem, Guillermo Restrepo, yeah. Yeah, Alan, thank you for your nice talk. And I have a question, and is that you showed that Meyer and Mendeleev, they made several changes to the original periodic system they published. Don't you think that they made those changes because the number of compounds that were reported with the time was also changing? I mean, whether they were adjusting the table according to the evolution of the, let's say, chemical space?
Yes, I absolutely do think so. And this is really the point that I was trying to make when I say you have to look at this in a careful, chronological, diachronic way, because that chemical space, to use your very fruitful way of putting it, that chemical space was constantly changing. And yes, you've got to look at how what they may have learned from each other, what they developed independently. Again, I'm just repeating myself, but also this month by month, year by year, accretion of new information, better atomic weights, better understanding of the properties. This is the point, especially that I was making with the boron group. Boron and aluminum were problems in 1861 and 62 and 63. Indium and thallium were just being discovered. And so, as I say, it's not surprising that Meyer chose not to try to create a group that we would now call the boron elements.
Yeah. Okay, thank you.
Okay, thank you. Shaw Cat, and I've lost the rest of the name. I'm sorry.
That's you. Okay, thank you. Thank you very much. Yeah. So I'm not a historian of chemistry. I'm coming more from history of physics, and my question is more methodological than on the subject itself. And I'm very interested in the cases of parallel discoveries or multiples or whatever we call them. And I'm a little bit wonder what exactly is the discovery here. It's not by saying that we must have, but if you can elaborate what your idea of discovery was here in a general and in particular, because you mentioned for one sense that the periodic table is, the full periodic table is Mendeleev. So this is the discovery of the periodic table. And then you mentioned some discoveries of, or predictions of elements, which you attributed to 2 of them. And in the meanwhile, you also use the differences between them to understand better each other, especially Meyer. You understand it was very interesting for me to see how you did use the graphic method is more efficient than the regular table writing to predict new things or to infer from it. So if you can elaborate on these questions, I'm happy.
Yeah, I think you're putting your finger on important point. The word discovery seems like a sort of a binary black and white kind of thing. Something wasn't known and now it's known. But mostly what the events that we're talking about can't be put in such clear terms. There were, partly because these were whole systems. This is why the phrase periodic system of the elements really is the right way to think about it. And systems have all kinds of different aspects and qualities. And as I pointed out before, heurisms. And so even the discovery of an element is a difficult, often a difficult idea to pin down, because it's often not a unit point in time. And there are often many ways to look at it. And we've tried to take account of these subtleties. So you're right to ask the question.
Okay, sorry, I skipped over because my chat feed keeps jumping. I should have asked Alexander Angerhoff to ask a question.
Yes. So the question was whether Mendeleev and Meyer actually corresponded with each other. Has there been any historic record of letters written between them?
Not that I'm aware of. That's Gisela, can you help me here? I don't think so. Gisela knows more about the actual correspondence.
I do not know. I haven't find any letter from Mendeleev to Meyer or from Meyer to Mendeleev. But it does not mean that there existed something, but we haven't in our hands.
Yeah.
Thank you.
You just hope somebody opens their attic at some point and says, "Oh, what are these interesting letters?" Bernadette.
You're muted.
Bernadette.
Okay. So my question is, we all know about the context of discovery of Mendeleev, in the course of writing a textbook. But what about the pathway, Meyer's pathway? I mean, what is exactly the place of the periodic system in his investigative pathway, if I take up Larry Holmes' notion of investigative pathway?
Yes, this is a very interesting question. We've tried to look at it. It really, it has a lot to do with Meyer's, well, how to explain this in short, in a short version, in Meyer's holistic way of dealing with the science of chemistry. So some of this came from his understanding, oddly enough, of organic chemistry. And some of you who've worked with the prehistory of the periodic table know that there was this curious relationship, the idea that the regularities in homologous series in organic chemistry reflected something about the triadic relationships in inorganic. And Meyer took this and others did too, to suggest that there was subatomic structure. In other words, that atoms were not the end, the last mode of analysis. There were subatomic particles. And so this whole idea of organic chemistry feeding in, and also the idea of understanding the intrinsic nature of atoms and whether they had subatomic structure, all of this led him. These were integral parts of his pathway towards the periodic table.
Okay, it means that he was an advocate of Proud's hypothesis, what you call subatomic.
He was a partial advocate. So In 1864, he was expressed doubt. In 1869, he was, in 1872, he thought it was more possible. A kind of a modified Prout hypothesis, he thought was maybe the way, the most probable way to understand atoms.
Okay, thank you.
Okay. John Christie, who's on YouTube, has a question, so I'll read that out. Do the predictions for the empty assignments provoke active search for their occupants, or are such discoveries more happenstance?
Sorry, the audio wasn't very good. Could you repeat that again?
Basically, John's asking, did those gaps in the periodic tables with those predictions meant that people went out and looked for those elements, or did it happen in any case?
So this is a question about the research pathway of Wadodran and Nilsson, the discoverers of germanium and gallium and scandium. And I can't really answer that. I don't know the answer to that. And perhaps Gisela has an opinion. But I don't know whether they discovered these new elements because whether they used Mendeleev's or Meyers' ideas to help them discover these elements.
I don't think they did, because they claimed they weren't looking for those elements. I think two out of three of those cases at least said they were not looking for that element. And they refused to believe it was that element initially.
Yeah. Thanks, Eric.
Gary Patterson has another question. Does considering the much larger community help us understand the evolution, presumed, of the periodic table?
The larger community of chemists. Yeah, I think it does. I think you have to, again, you have to view these things in ways in terms of interacting groups. And of course, we've concentrated on Meyer and Mendeleev here, but there was a whole community. Meyer and Mendeleev may not have corresponded together, but Meyer certainly corresponded with many others. And I do think you have to look at this in a group fashion. Yeah, so the answer is yes.
Good. Peter Ramberg.
I just had a comment that I wrote down that I happened to be looking at Scientific Babble by Michael Gordon. He notes in the Mendeleev archive, there are only two instances of Meyer correspondence from the 1890s. One is from his widow, telling Mendeleev that Meyer has just died, and the other one is from Meyer. So those are the only two that, and that's, for what it's worth, that's what I know.
Okay, thank you, Peter. That's helpful.
Okay, Hassett Chang.
Yes, thank you very much, Alan and Gisela, for that instructive talk. I wanted to ask you if you could expand a little bit on the atomic volume issue, right? And particularly how exactly knowing about the periodicity of atomic volumes helped Meyer, and why Mendeleev, having only the non-graphic form, didn't have the full advantage of that.
Yeah. So here is the atomic volumes curve. And you see the regularity of these segments is really quite remarkable. And you see the writing here. You can't read it unless you get very close to it. It's not visible in this image. But he talks about the properties of these elements here along these curves, and they So if you have a certain segment here and another segment here, there is great physical and chemical similarities between the elements in, say, this particular portion of the curve and this particular portion of the curve. You see these kinds of parallels so clearly in a visual image, and they are not nearly as clear in simply a table of data. So Mendeleev developed the table of data. He thought it was important. You could learn certain things from it, but this is a far more dramatic way of understanding the periodicity, and you can take it apart in a more helpful fashion. You can use it to understand some of these details in a more fine-tuned way. To get into the details, to answer your question properly, would take getting into a lot of weeds here. Yeah. that I don't really have time to do. But just to qualitatively suggest, this is the answer to your question.
Right. Thank you.
Okay, thank you. We've still got time for perhaps one or two more questions. So while somebody thinks of a question, I'll ask another one that occurred to me. Davy, having discovered, this is way before you, but Davy, having discovered sodium and potassium and all those sort of elements, was actually very upset that he was adding more and more elements, more and more chemicals to the list of substances that existed. And so he sort of tried to sort of work out that sort of combination by simply by properties of the chemical properties, in order to try and group them, in order to try and find some commonality, as if there was something behind them. Do you think that had any sort of resonance with what with Meyer and Mendeleev, sort of trying to sort of reduce the number of entities and real entities in the world, so to speak?
I'm less expert about Mendeleev, but I can tell you that Meyer definitely thought that the multiplicity of fundamental parts of nature, the elements, suggested strongly that they were not the truly fundamental parts of nature. So 60 plus elements, he like Davy, they both had the same reaction. There can't possibly be 60 fundamental parts of nature. There must be something more fundamental behind them, inside them. And this was a strong reason, one of many, but a strong reason, sort of a overriding ontological reason why Meyer was convinced that subatomic particles must exist.
Right. Good. So one final question from Sarah Hymans.
Yes, thank you. This is really interesting. So since we already had one question about correspondence and then another question about the larger scientific community, I was wondering, did either Lothar Meyer or Mendeleev correspond with anyone else about classification of elements or periodic tables? And did that help them develop their classifications? If they didn't exchange between them, did you come across any of these kinds of letters?
Not specifically. I'm not aware of specifically correspondence specifically directed towards the periodic system of the elements. But again, I turn back to Gisela, whether Gisela might know.
Of course, there was correspondence where Lothar Meyer mentioned his periodic table, but not in such a connection that he discussed with colleagues his findings. But he also gives the information. Later on, in connection with the discovery of the germanium, there was a correspondence between Meyer and Winkler concerning this discovery, but and Lothar Meyer used in this case, of course, his periodic table and especially his atomic volume curve to show that this new element must be the Aker silicon, but it's not directly connected with the established or with the erection of the periodic system.
Right.
Okay, thank you.
Okay, so with that, I think I'll draw the seminar to an end. Just a couple of announcements for the next parts of Jacques' program. On the afternoons of the 14th and 15th of May, we will be running with the World Photographic Society a joint meeting to mark the 250th anniversary of the birth of Tom Wedgwood, who, among other things, invented a very early form of photography. That's being announced on various bulletin boards at the moment, but if you'd like to look at the website, which is actually a very easy address, rps.org/Wedgwood 250, which is all one word, you can find the program and registration details. And because we're running that two consecutive afternoon meetings, we will not be having a Jacques seminar next month. The next Jacques seminar in this series will be by Robert Budd on the 17th of June, and that will be advertised nearer the time. So it just remains for me to thank the production team for this seminar. That's Anna Simons, Joe Henderson, and Becky Martin. And finally, to thank Alan Rocke for giving a really stimulating, thought-provoking, and wide-ranging discussion on how the periodic table came into existence. So thank you, Alan, and thank you, everybody, and have a good evening or night or wherever you happen to be at the moment.